All right, so now we're going to look at a way to pick objects or elements out of a set such that the order does not matter. With permutations, the order was important. With combinations, the order is not important. And you can think of this like the players on a basketball team. Let's say you went to your city park and there was outdoor courts there, and 10 people showed up to play ball, play some pickup game or something. You got 10 players that want to play 5-on-5 basketball. You got to pick teams. The order in which you pick the players for each team doesn't matter. I mean, it does to them because they want to be picked first. But in the end, the team is the same regardless of what order the players were picked. If I'm a captain and I pick Teddy before Jimmy, it doesn't make a difference, for my team if I pick Teddy first or if I pick Jimmy first and then Teddy later, as long as it's the same players. Now again, to them, they may feel better about being picked first, but in the end, the team is still the same, so the order doesn't really matter. And so that's what we're looking for is combinations here. Now, how could I pick, how many different ways can I separate these teams? That's what we're looking for with a combination. So, and this is a good example to start with. If I were to take 10 players and do 2 teams of 5, well, one team of 5 and then the rest on the other team. So really you're picking one team and then the other team is just the remaining players. So the way that we would set this up and what we're going to do with combinations is we're going to say that this is 10 choose 5. So you start with 10 players, you choose 5 of them for a team. The other team is the remaining players, okay? So you're really just choosing the 5. You're not choosing all 10. You take 5 off and then separate the other 5. Okay, so the way we write this, the notation is kind of like the permutations, except we use a C instead of a P, right? Combination instead of a permutation. It's 10 choose 5. And you're just choosing 5 with no order. The order is not important. Now, if the order was important, it'd be a permutation, and the formula for that would be, if this was 10p5, then the formula for that is 10 factorial over, no. Well, it is 5 factorial, but it's 10 minus 5 factorial. You do the subtraction between the two, which ends up being 5 factorial, but it's the other 5 anyway. And so here it ends up being similar, except you end up with fewer examples. You end up with fewer distinct combinations than you do permutations, because if the order is important, then every particular order in which you pick the players counts as a permutation, whereas all of them grouped together, with the same team, all the orders grouped together give you the same combination. So there's fewer combinations and permutations, and the way you get the actual number is by taking the permutations and dividing out another 5 factorial. And so the formula, in this case, it would be 10 factorial over 10 minus 5 factorial times the remaining 5 factorial. So as a general principle, if you take n choose r, the formula is n factorial over n minus r factorial times r factorial, right? So it's in this case, both the n minus r and r happen to be 5 because I split the teams evenly. That wouldn't always be the case. So in this particular example, we would have 10 times 9 times 8, 7, 6, and then I'll stick a 5 factorial because I know that's going to cancel with one of the 5 factorials in the bottom. This here is again 5 factorial times 5 factorial when I simplify. So I've got one 5 factorial, I'll just cancel out at the end. The other 5 factorial is 5 times 4 times 3 times 2 times 1. And I'm just going to write it all out so that I can easily cancel stuff. Okay, so let's see. The 10 cancels with the 5 and the 2. The 4 cancels with the 8, or reduces to make it 2. And the 3 reduces with the 6 to make it 2. And so the 1 is the only thing left on the bottom. And on top here, I'm left with 9 times 2 times 7 times 2. That's, let's see, that's 63 times 4 over 1. And 63 times 4, that's 12, and 240 is 252. Yeah. So that's 252 different combinations. So if I had a set of 10 people, I wanted to get 5 of them on a team and 5 on the other team, there's 252 ways to do that. Okay. Again, the order doesn't matter. The order in which you pick them doesn't matter. Okay. If you wanted to compute, 12, choose 3, for instance, if I had a set of, if this was 12 faculty in the math division, which it's not 12, but if there was 12 faculty in the math division and you had to put 3 of them on a committee, how many different ways could you do that? Again, the order in which you choose them doesn't matter. And so the formula for that is it would be the 12 factorial over, now you get n minus r, which would be 9, right? 12 minus 3 factorial times 3 factorial. So the n is 12, the r is 3, and then you just have to evaluate it. So it's 12 factorial over 9 factorial times 3 factorial. You can do a lot of canceling on this one. The 9 is really nice here. So I've got the 12 is 12 times 11 times 10, and then you get a 9 factorial, which I know will cancel with the other 9 factorial on the bottom. This 3 factorial, I'm going to write out 3 times 2 times 1, and then I can cancel the 3 and the 2. That makes 6. That cancels with the 12 and makes it 2. And so, right, 12 over 6 is 2. And then I get 2 times 11 is 22 times 10 is 220. So there'd be 220 ways to choose those people. Essentially what you're doing, if let's say it's the math discipline faculty and you're throwing 3 of them onto some committee, and it doesn't matter the order in which you pull them, the committee is the same, then what you're doing is you're taking the 12 total faculty and you're dividing by the 3 being chosen for the committee and the 9 not being chosen, and the factorials for each of those numbers. Okay, so anyway, so you get 220 total combinations for choosing those committees.